Good afternoon, everyone, and welcome to the June Food for Thought seminar. I'd like to begin by paying my respects and acknowledging the traditional owners of the land on which we meet today, the Whadjuk Noongar people of a proud Noongar nation. And we recognise their ongoing connection to this land and their contributions to the life of our city and state. Before I introduce today's speaker, I'd like to share an update from the Foundation, as I usually do. Earlier this week, I hope you've all seen that we launched our 2025 Ignition Grants Program. This has got a focus on advancing healthcare, knowledge and acquisition, and is supporting a pathway to research success. Grants will also support early and mid-career researchers pursuing novel ideas and will facilitate early-stage research that has a clear pathway to clinical application. This program is actually continuing our legacy by providing seed funding for innovative research projects that have a strong connection to the East Metropolitan Health Service. Applicants are able to request grants of up to $100,000 for individual projects of up to 2 years in length, and applications will close on Monday, Wednesday, the 2nd of July. So I do encourage you all to have a look at our website where you will find the details, and details also will feature in our next edition of our newsletter, The Signet, and please do use the QR codes available at the back of the room to register for our regular newsletter so that you can stay up to date with this and other funding announcements. It's now my pleasure to introduce today's speaker, Professor Bronwyn Stuckey, AM. Professor Stuckey is Medical Director at the Keogh Institute of Medical Research, Consultant Physician at Sir Charles Gardner Hospital, and Clinical Professor in the Medical School at UWA. She's a past President of the Australasian Menopause Society, a life member of the Endocrine Society of Australia, and a member of the Order of Australia. And many thanks, as usual, to Professor Marcus Schleich, who will facilitate the Q&A session and officially close the event. Please join me now in welcoming Professor Bronwyn Stuckey and her presentation, From Pulses to Flushes, A Journey Through Reproductive Life. Thank you.
Thank you very much for that introduction, and thank you to Marcus for inviting me. This is not very hypertensive, this talk, so yeah. I'll just see if I can, this will be not a straight line, this talk. It'll be back and forward. A lot of it is serendipity rather than strategy. A lot of it is history rather than hypothesis. There'll be flashbacks, flash forwards, and at the end we'll have some hot flashes. So I've received honoraria from Astellas, which is relevant to this talk. I thought I'd just tell you about the Keogh Institute. The Keogh Institute was set up as the Reproductive Medicine Research Institute by the late Professor Ted Keogh, and it was set up in 1983, and when he died in 1995, I inherited it as the medical director. And the structure of the Keogh Institute is that we look at male and female reproductive endocrinology. We have a clinic where we see patients, clinical care, and we have a research area. And the theory is, the hope is that what we see in the clinic will be the subject of research, and what we do in research will go back to the clinic and help patients. So this is my first slide, and this first slide is just to judge the tenor of the audience and to see if you have got lateral thinking, and to also introduce negative feedback, which is probably not appreciated by chefs but very much appreciated by endocrinologists. So reproductive endocrinology in particular has two tenets central. The first is negative feedback control, and the second is pulsatile hormone delivery. So if we look at negative feedback control, so this is obviously male brain, not to scale. And testosterone and sperm production go on pretty well. There's a little bit of up and down from morning to night in testosterone, but actually that is repeated, same daily repetition. In older men it gets a bit lower, but there's no chaos in it compared with female reproductive endocrinology with the pink brain. The same system, the same gonadotrophins run the gonad production, the gamete production, I should say, and the hormone production. So LH stimulating hormone release from the ovary, and FSH stimulating ovarian oocyte development. But you can see on the left there that that's a chaotic up and down over the month. And the female menstrual cycle is, I think, the most difficult to understand. How does it happen? When you talk to a patient and you say, do you have regular periods? Oh yes, every fourth Friday about 4 o'clock my period starts. I mean, how does that happen? I think it's much more understandable if people don't have regular periods. But the way that the hypothalamus, the pituitary, regulates this absolutely regular menstrual cycle is what started all this research. And that research started with the discovery of pulsatile hormone delivery. And Ted Keogh was right at the beginning of this research. He did his postdoc in Pittsburgh with Ernst Nobel and was right at the beginning of discovering how the hypothalamus controls the pituitary. So this is a quote from the musical Sweet Charity. And so those of you who are cardiologists will understand the pulsatile nature of the cardiac rhythm. Those of you who are interested in adrenal function and jet lag, for instance, will understand the circadian rhythm of the adrenal gland. But what controls the menstrual cycle? So we should start with the discovery of the hypothalamic peptides. So in 1971, Gierman and Shelley independently, not collaboratively, and sometimes acrimoniously, discovered the hypothalamic hormones that run, for instance, the thyroid TSH, the thyroid-releasing hormone that runs TSH, and also LHRH, the GnRH molecule, the decapeptide, that runs the pituitary sex steroids, the pituitary gonadotrophins. And they received the Nobel Prize for this in 1977, and Rosalind Yalow shared it for the radioimmunoassay of peptide hormones, which gave Ernst Nobel and his laboratory the armamentarium to look at what controls reproductive function. So his goal was to understand this mystifying menstrual cycle. And his model was macaque monkeys, ovariectomized macaque monkeys, and looking at the oscillations of the pituitary hormones. So in 1970, his lab published a paper in endocrinology demonstrating that LH has oscillations of roughly about 60 minutes, measurable in the circulation. But he had a lot of trouble working out how GnRH achieved this. So GnRH stimulates LH and FSH. He'd already looked at the oscillations of LH in the circulation. But when he got his hands on GnRH, he gave it in a continuous fashion. And this is a great paper by Plant, absolutely great paper. It sort of gives you a bit of an idea of the personalities and the politics and the to's and fro's, the fails and the successes of a research laboratory. So he tried GnRH continuously he had monkeys where they had radiofrequency lesions, isolating, removing their own hypothalamic control of the pituitary. The pituitary was intact. They had no ovaries, so he'd removed feedback, negative feedback. And what he found was, if he infused GnRH, there was an immediate FSH-LH surge, but it was unsustained. And it was not until Japanese researcher Nakai suggested that there might be a loss of second messenger responsiveness if you continually exposed it to GnRH. So he suggested that they used pulsatile GnRH, which apparently Nobel rejected it, and Nakai said it was because his English was poor and the chief didn't understand biochemistry. So we come to this seminal paper in Science in 1978, where Ted Keogh was a co-author, where it was demonstrated quite clearly that if you gave pulsatile GnRH, you had pulsatile LH. If you gave continuous GnRH, you switched it off. And if you then came back and gave it pulsatile again, it recovered and the pituitary responded. So having discovered this can go in two useful directions. Either you can take the model of pulsatile GnRH in the clinic, or you can take the model of continuous GnRH or GnRH analog, which is does similar things. So, Ted Keogh was pretty smart off the blocks, I should say, in using this, and so was David Hurley. If you give ovulation induction with clomiphene to somebody who has very, very low estrogen, what you are doing with clomiphene is to block the negative feedback. And if I can just think of the pituitary as a sort of person for a minute, the pituitary thinks, no estrogen, I will put out my messages down to the ovary to stimulate the ovary. That's how clomiphene works. But if you have a patient who has very, very low estrogen, the pituitary is used to seeing no estrogen, so clomiphene doesn't work. Gonadotrophins, on the other hand, completely bypass any negative feedback control. So if you give gonadotrophins for ovulation induction for fertility, you have the risk of hyperstimulation and multiple ovulation, multiple pregnancies. So these three papers, published pretty soon after 1981, 1983, 1984, demonstrated that pulse GnRH would switch on the pituitary and induce ovulation in women with amenorrhea and infertility. And this is the original pump, invented by Ted and Atikuzal. It's about that big. You load up a syringe with GnRH, you put the scalp vein under the skin, and every 60 to 90 minutes there's a whirring sound, and it just advances the plunger forward a little bit. So pulse GnRH then was used for induction of delayed puberty, induction of ovulation, induction of spermatogenesis in men. But I want to talk about this one, cryptorchidism. The descent of the testis is essential for the ascent of man. there are two phases. One is the transabdominal phase, which is depends on genetic and anatomical factors, but the crucial phase 2 is where the testis abseils down into the scrotum, guided by the gubernaculum, which, by the way, my husband says is the word for rudder, so I don't think that's really a rudder. Is it, Gerald? No. So you can imagine, if it depends on testosterone, then cryptorchidism is associated with lots of conditions where there is disorders of where there are disorders of sex development, including Klinefelter's, but including, crucially, what we're interested in is congenital hypogonadotrophic hypogonadism. The chromosomes are XY, but the problem, the testis is okay, or could be okay, but the problem comes from the hypothalamus or the pituitary. And so this is these are the red flags of congenital hypogonadotrophic hypogonadism, which I'll call CHH for stopping so many syllables. There's signs of absent androgen action in the baby. So micropenis, cryptorchidism, delayed puberty, or mixed, and the mixed includes micropenis and cryptorchidism, hypospadias, micropenis and hypospadias. So when a baby appears with these signs, these should be red flags that there is something wrong with the androgen production, and possibly with the hypothalamus. And since 1991, there have been multiple genes identified that interfere with this crucial pathway, starting off with what's now called ANOS1, which used to be called CAL1 for Kalman syndrome, and there's probably more. And I want you to keep this diagram in mind. So this is a good diagram showing you where these genes operate and where variants in these genes cause trouble. So here is the level where the GnRH neurons come down through the olfactory placode, through the cribriform plate. That's the first stage of GnRH neuron migration. That's all right. And so you would expect that somebody who has a mutation in this gene has anosmia, as well as other things, as well as a hypogonad, as well as CHH. Whereas mutations in these areas, these stages, where the kidney neurons are operative, or where the pituitary or its receptors are operative, you don't expect anosmia. And in fact, Kalman's anosmia is a sine qua non of Kalman syndrome. So Ted decided he would treat cryptorchidism with pulse GnRH. And this is the hypothesis that physiological pulse GnRH in boys with cryptorchidism would stimulate pituitary LH. Pituitary LH would stimulate testicular testosterone production, and that testosterone production would induce abseiling of the testis down into the scrotum. So there's the pump. You can imagine the job description for the research assistant must be good with kids and must be able to sew. So the pump, there was a little pocket in a vest. The pump was put in a little pocket, and the catheter and the scalp vein needle was put under the skin, and the parents were taught how to do this. Took it off when they bathed the baby, and the pump delivered 60 to 90 minute GnRH pulses. And this is one of these little boys. So he treated 98 boys. There was pretty wide age range, and getting out to 13s are getting a bit stretching the limits. But the result, which I'm going to brush over because that's not the point of this, is that the testes descended in 45% of boys with this treatment. Pretty short amount of treatment actually, 3 to 16 weeks. But I'm just going to introduce you to this little boy, fast forward 33 years, and David Hurley referred him to me for induction of spermatogenesis. And he had a history of micropenis and cryptorganism at birth. He presented with azoospermia. He'd had failure of puberty and had had testosterone treatment since the age of 16. And he had anosmia, and Kalman syndrome was confirmed by an anos mutation, pathogenic anos mutation. When I met him, he had a small right testis, about 6 mils in the scrotum. The left testis was still up in the inguinal canal. And I said to him, we can do it, but you have to be patient, because in the literature and in our own experience, it takes 15 months for one sperm to appear in the ejaculate. So what we do is we give HCG, which acts as LH, to induce intertesticular testosterone production, and we use FSH to induce spermatogenesis. And so why does it take so long for men with CHH to achieve spermatogenesis with induction? It doesn't take that long for people who've had a pituitary tumour and had the pituitary grubbed out, and you give them the same treatment. That switches on pretty quickly. And the reason is because they lack mini-puberty. So what is mini-puberty? So what normally should happen after the baby's born and the mother's estradiol's washed out of their system, the baby's GnRH pulses stimulate LH and FSH rise, and the testosterone in a baby, between 2 and 10 weeks, can rise up into adult male levels. That's one thing, but the crucial thing is that the surge in FSH at this time stimulates a proliferation of Sertoli cells within the testis. And Sertoli cells are termed the nursemaids of spermatogenesis. They are critical for sperm production in later life, and because each Sertoli cell can only support a finite number of germ cells that go on to produce sperm. So in Kalman's and other forms of CHH, there's no mini-puberty, there's no puberty for that matter, and so they miss out on this crucial stimulation where you get the surge of gonadotrophins, a very finite period of time, and then that all settles down until puberty, and they should come up again. So at 12 months, CJ had a total sperm count of 25 million. Well, that's a surprise, what's going on there. And I had a talk to him, and I realised that he was part of Ted Keogh's cohort of boys who'd received pulse GnRH in infancy. And so the hypothesis, which I think I've got on the next slide, so the hypothesis is that even though Ted was thinking he was just giving LH testosterone to testicular descent, in fact he was also giving FSH to Sertoli cells and support for his future spermatogenesis. In fact, what he was doing was replicating mini-puberty. This is an advertisement. This is James Nolan, who you may or may not know. So James is starting his PhD on CHH and mini-puberty with the aim of identifying infants with the red flags that suggest they have CHH, and developing a protocol which we hope will be around Australia for replication of mini-puberty. And James is, I don't know how old he is, but he's young enough to see the results of his work in 30 years' time, we hope. Okay, so let's go back to this and look at continuous GnRH or GnRH agonist. What about if we use the switch-off properties of GnRH? We were onto this too. So this is from, when's this from? 1987. Okay. So we had 6 women with polycystic ovary syndrome, and we used GnRH delivered continuously this time via the pump to abolish the LH pulses, suppress the androgens, and then we used gonadotrophin stimulation for ovulation induction. So this is really a prototype for the future development of GnRH agonists. So I'll just introduce to you GnRH agonist. So this is the GnRH decapeptide, very simple. It has a binding site and an activation site, and the cleavage point, which is essential for the on-off sort of action of GnRH, is here between glycine and leucine at position 6, 7. So by substituting an amino acid that is resistant to the cleavage, you can produce leuprolide or goserelin, which is also called Solidex. And of course, we know this has got lots and lots of clinical applications: precocious puberty, downregulation of the gonadotrophins in IVF, just the way we use continuous GnRH, and also hormone-dependent cancers: breast cancer, endometrial cancer, prostate cancer, endometriosis, and suppression of ovarian androgens. And this very troublesome thing here, premenstrual dysphoria, which is a nightmare, responds very well to GnRH analogue by completely switching off the chaotic hormones that occur at perimenopause. And also we've used it for cyclical immune dermatoses. So this is catamenial erythema multiforme major, which completely resolved when we switched off the ovarian cycle. Let's go back a bit. This is a flashback this now. So the question is, how does one GnRH decapeptide operate through one gonadotroph and produce differential secretion of 2 gonadotrophins, LH and FSH? So I'll introduce you to 2 patients, which we see all the time, Caris. Miss PCOS, Miss HA, hypothalamic amenorrhea. Both have amenorrhea. Miss PCOS has a BMI of 27. She has an LH of 12 and an FSH of 4, and she has a high free androgen index. Miss HA exercises a lot, almost probably vegetarian, possibly even vegan. She has a BMI of 17. She has switched off her LH, but her FSH is sort of getting up towards the top of the reference range. So how does that happen? How do you have that sort of differential response when you've only got one GnRH peptide, you've only got one gonadotroph? So it's all to do with frequency. So we know that LH and FSH have identical alpha subunits, but they're distinguished, as are HCG and TSH, by the beta subunit. So you can distinguish them by their beta subunit. So how does the pituitary switch off one and keep going with another? And it's all to do with the GnRH pulse frequency, which I have to go back to rhythm. So if we're andante, nice walking rhythm, we have LH and FSH produced in relative equal amounts. If you ramp up your pulse frequency, allegro, then you preferentially produce LH beta subunit, and if you go slow, you preferentially produce FSH beta subunit. So that's the way you get differential production of LH and FSH from the pituitary. And of course, what happens at ovulation is at ovulation, the pulse frequency of the GnRH causes preferential LH secretion, and you get the LH surge for ovulation. I won't say that. I was going to say, I will say. I also think when we look further on about what's happening with thermoregulation, there might be more going on with what's happening in the hypothalamus, with the temperature. You know how you do temperature regulation to see if you ovulated? If we go back to here, much of what we've learned about the control of reproduction and the HPG pulse, hypothalamic pituitary gonadal pulse generator, has come from the genetic, what we've found with the genetics of people whose HPG axis isn't working. In particular, the level 2, which introduces us to the Kindi neurons, or the Kandi neurons, whichever way you like to pronounce it. So we know that GnRH is released in pulses. So how does this work? Well, it works because there's an on-off switch in the Kindi neuron region, where neurokinin B is the on switch, dynorphin is the off switch, and these function as paracrine, autocrine, endocrine regulators, particularly autocrine regulators. And so the neurokinin B releases pulse kisspeptin, which releases pulse GnRH and pulsed gonadotrophins. So the neurokinin B's switch on, dynorphins switch off, switch on, switch off, and you need that on-off for the pulsatile secretion of kisspeptin and GnRH, which brings us to menopause. Okay, so there are two views of menopause published in The Lancet last year. One is that it's healthy ageing, that it's not an estrogen deficient state, that is over medicalised, and the best thing we can do is to empower women to get over it. My view, obviously, is different. It is an estrogen deficient state. It's the result of medicalisation of the hazards that women have previously undergone, including childbirth, peripartum infections, contraception, stopping us being exposed to hazards of multiple pregnancies. And it's a iatrogenic condition, basically, because it's prolonged life past 50 years. I suppose what's not arguable, what's not at a controversy, is that it's associated with hot flashes. which I think are probably contributing to global warming almost as much as methane from the cattle industry. And it's characterised by raised FSH and hot flushes and other unpleasantries, which we won't go into at the moment. So if slow pulses favour FSH, what favours FSH at menopause when the FSH rises? And it's not because of the frequency, but it's fortissimo. So the pulse amplitude is increased, not the pulse frequency. How does this happen? So I will introduce you to Naomi Rance from the University of Arizona, who's done so much work in the kindy space and hot flushes. And she has said that her interest in the area started when she had her first hot flush. So this is a hot flush. What happens is the core temperature rises. The tolerance for core temperature variation has been reduced in menopause, and as soon as you get to this trigger, then you have a hot flush, and there's rapid cooling. And anybody who's talked to a menopausal woman will hear the same thing. Oh, I was in bed at night and I got this terrible hot flush. I threw the bedclothes off, and then I got incredibly cold and I had to pull the bedclothes off, and my husband complained, and then why don't you go and sleep in another bed, and that sort of thing. So what Naomi found was, looking at the hypothalamus in postmenopausal women compared with premenopausal women, is she found increased staining of kisspeptin RNA, and the kisspeptin neurons were hypertrophied and displayed increased gene expression. And when she did photomicrographs of neurokinin B, the one that switches on gonadotrophin pulses, she found the same thing, that there was increased gene expression. Therefore, it's the increased numbers of the kindy neurons that are responsible for the increased amplitude of GnRH pulses and the raised FSH. Well, that's all and good, but are kindy neurons responsible also for hot flushes? So the hypothalamus is the obvious place to look for this, because it's the mediator of the defensive the core temperature. So you have the hypothalamic neurons going out to the sympathetic preganglion neuron, and except in Eskimos, who have a lot of brown fat, vasodilatation and sweating are for cooling, and shivering is for warming, all mediated via the hypothalamus. And I think you might find that if you've got patients who've had, for instance, a craniopharyngioma where the neurosurgeon has grubbed out a bit too much of the hypothalamus, then often they're insensitive to hot and cold. We've found that the kindy neurons have neurokinin B has a projection to the thermoregulatory centre. So this started off a lot of very elegant experiments involving rats who don't have a head hot flush, they have a tail flush. And it was found experimental ablation of the neurons in rats not only eliminated the LH rise after the ovaries were removed, but it reduced tail temperatures, so they had no hot flushes. Conversely, if you administer neurokinin B, it raises the tail temperature of the rat, and they have a hot flush. So very elegant experiments, but of course, if you write a paper, you've got to say, limitations, the limitations of this paper were. And what Naomi Ranson says was a major limitation of our research is the rat could not report the hot flushes. But women can. And so the experimental evidence in humans were done with premenopausal women, so estrogen replete, in a climate-controlled room, and they had 30 minutes of infusion of either neurokinin B or placebo. And they had subjective report of hot flushes plus measurement of skin conductance. And these are the results. So, so the black is during placebo, and the red is during neurokinin B. And you can see that neurokinin B produced hot flushes, and the vehicle did not. But you also notice that there are two very problematic patients here who didn't have hot flushes with either placebo or neurokinin B. And they're the sort of women where you're in a coffee group, I get terrible hot flushes. Your periods, yes, my period stopped. I didn't feel a thing. My periods just stopped. And of course, they're not invited to the next coffee group because they're not sympathetic to the chaos that's going on. So is there a missing link mediator? If it's the missing link, why do some women have horrendous symptoms and some women have nothing, even if they have raised FSH? So if we look in this, where the Kindy neurons are, the TAC-R3 and TAC3 are the genes that code for neurokinin B and the neurokinin receptor. So this study here from the from the nurses, from the Women's Health Initiative study, which gave us a lot of problems but given us some good data, asked, is there a hot flush gene, and if so, where is it? So this is where it is. It's in the meta-analysis, the relationship between the genetic variation in TAC-R3, which codes for the neurokinin B receptor, was associated with hot flushes. So presumably that's a gain of function variant, and presumably people who don't have hot flushes as a problem at menopause have a loss of function receptor. So if we know that, then the Kindy pathway is an attractive target for non-hormonal control of menopausal vasomotor symptoms. And this is the first paper that came out. This is, it was called pavilinetant, but in this paper it's just given a number. Published in 2017, 37 postmenopausal women with a lot of hot flushes, randomised in a crossover study to placebo or a neurokinin receptor antagonist. That's the design of the study, 2-week washout in the middle of it. And I think, this is the problem with menopausal, placebo response is always very good, but there's a significant difference between the active and the placebo, both in both whether you had the placebo first or second. However, there was a problem in that 3 participants had a pretty substantial rise in the liver enzymes, which is a sort of death knell to any drug development, and so this was cancelled. And we're all very, very despondent about this because there are so many women with breast cancer who have terrible hot flushes who can't take estrogen. So it took 7 years. This is our paper where this is fossicking around in the Kindy space too. This is a molecule that is not a neurokinin 3 antagonist. The company's pretty sort of coy about where it is in the kidney space, but that was a pretty good reduction in hot flushes with this medication. But in 2023, fezolinetant was reported in the Skylight study. Our study included breast cancer, people on adjuvant therapy for breast cancer. This study did not include breast cancer patients. And it was a 12-week placebo-controlled and then 40-week active drug. And I'll just walk you through this. So this is the placebo, again showing a placebo response, but not as good as the fezolinetant response. And then here's when it's switched over to open label. And this is the frequency of hot flushes, and this is the severity of hot flushes. So no doubt effective, but the liver transaminase cloud is hanging over any development of neurokinin receptor antagonist studies. So the researchers, the pharma, made a point of doing a safety study. Lots of women, placebo, 2 doses of fezolinetant, and 52 weeks, just to make sure that there was no liver signal. And so this is the transaminase cloud, if you like. So up here is the no-go zone. Any patient that 1 patient is worrisome, 2 patients, it's a death knell for the product. And fortunately, no patients had the ALT, AST of over 3 times, or bilirubin over twice. and it was good because this study included people who you might say would have deranged liver function tests, people with obesity and a non-alcoholic fatty liver. So this has been approved in Australia. It's not on PBS, unfortunately, and unfortunately there are no data in breast cancer patients that we can put towards the PBS in order to get it on PBS for breast cancer patients. And I really like this a statement by Paul Stewart, the editor of JCEM, acknowledging that the whole of this has come from our understanding and our investigation into a non-syndromic hypogonadotrophic hypogonadism and its genetic etiologies. I should say this is $425 a month in the US. It's $60 a month in Australia. Okay, so I hope I've shown you that the timeline, GnRH structure identified in 1971, or at least the and the importance of the pulsatile nature of it, discovered in 1978, with Ted Keogh being right there at the beginning. The usefulness of the pulsatile GnRH, but also the development of the GnRH agonists to switch off pituitary gonadal function. How we understand what is the differential gonadotrophin release mediated by pulse frequency, and how Kindy neurons provide the on-off switch that brings in the GnRH pulses. And we've discovered what causes, I think we've discovered what causes hot flashes, temperature instability in postmenopausal women, and through that the development of the neurokinin B antagonist for menopausal hot flushes. And now we have the Cauldron Club. Caris is a member of the Cauldron Club, and in our cauldron for the management of menopausal women, we have estrogen, fish oil, calcium, splash of gin, and now a neurokinin 3 receptor antagonist. Thank you.
Bronwyn, thank you so much for guiding us through. I know now why I didn't choose endocrinology. I couldn't pronounce half of the words probably you mentioned today, but amazing to see human physiology, the circadian patterns, and thank you so much for sharing all that knowledge on all the things that happened here in Perth, which is just amazing, and the Keogh Institute, of course, being testament to that. We have a lot of interest in the sympathetic nervous system, and I wondered, in terms of menopause and a lot of things you touched upon, how does stress and how does sleep deprivation kind of impact on it, on those patterns? Is it a bit of a hen or the egg question as well? I guess they can influence each other in both direction, but stress in particular, menopause and cycles. What's the role of stress in that context?
Well, I don't know about stress. So insomnia is one of the central symptoms of menopause. People talk about hot flushes, but and people say, okay, you get a hot flush in the middle of the night and that wakes you up. But I don't think that that the insomnia is necessarily dependent upon the hot flushes, because a lot of people who have got over their hot flushes still have insomnia with a lack of estrogen. And in fact, the neurokinin B pathway. So we're about to do a study looking at the effect of the neurokinin fezolinetant on insomnia. So I think there's probably yes, stress causes. I think probably that pathway is related. Now I'm sort of looking at that diagram where you've got the neurokinin B impacting on the sympathetic nervous system. Yeah.
Yeah, the hypothalamus is the super controller essentially of
yes,
of
yeah.
our cycles.
And of course the other thing that is a really common symptom in menopausal women is palpitations. So where does that come from? I mean, I presume that it comes from sympathetic dysregulation, and in fact, because I've had patients admitted to a cardiology ward, whereas in fact it's menopause, that's the problem. The other data that are interesting are the ones from Tommy Makola in Finland, where he, with their data linkage studies, they looked at women who continued menopausal hormone therapy versus women who stopped, versus women versus the population, and they found a huge upswing in cardiovascular deaths with people who stopped, and I suppose the theory is that's sort of dysregulation of the sympathetic.
Very interesting. Any questions from the audience? If not, I've got another one, and then I'll hand over to Laurie. The new medication for the hot flushes, is that to be prescribed by endocrinologists, or is that for general practitioners?
General practitioners,
as well?
yeah.
So no safety concerns? And
okay, safety concerns. So look, I'm...
Shouldn't have said that.
Oh, look, I'm pretty relaxed about it. I mean, I'm pretty convinced by their very well conducted safety study that showed no elevation of the liver enzymes. But of course, the company's got nervous about it, and so they've said, oh look, you must do liver function tests before, and then you must do liver function tests at 3 months. I mean, personally, I think that's just introducing ascertainment bias, because people do other things. They take herbal stuff. They have alcohol, and of course it's a bit like the romosozumab and the cardiovascular data, I think, that you're just biased now in what you see. You're doing liver function tests in people who are on fezolinetant, and then the companies, you must do this, that, and the other.
Laurie.
Thanks very much, Bronwyn. That was a lovely exposition of that story, and I particularly liked again, it sort of breaks down the barrier between so-called basic and applied research. What seems to be basic at the start leads to A, predictable outcomes, and B, unpredictable benefits. But my question is, sleep apnea is very common. Is there any impact studied of sleep apnea on hot flushes or on the pathways leading to hot flushes?
Okay, that's a difficult question to tease out. So there is no doubt that sleep apnea and disordered breathing at night is more common in the postmenopausal woman than the premenopausal woman, and you'd have to say that you'd think that that's to do with a lack of estrogen. I'm not sure I've got my finger on exactly what it is. I mean, the other thing, of course, that happens inevitably in women who, especially those who don't take menopausal hormone therapy, there's the glucose metabolism. You lose insulin sensitivity. You put on weight centripetally, and people put on a lot of weight over menopause, which of course contributes also to sleep disordered breathing.
I wondered whether any of the trials of reversing sleep apnea by mechanical or other means had studied the effect on hot flushes as a result in women who have hot flushes, I suspect.
I don't know about that. I know that we've looked at testosterone in men with the octopus CPAP.
Well, tirzepatide is now approved for the treatment of obstructive sleep apnea, interestingly enough. Tirzepatide, the GLP-1, GIP combined drug, Mounjaro here in Australia, which is, I think, remarkable, but that would be an opportunity to actually study in perhaps postmenopausal women the impact on flushes. Please join me in thanking Bronwyn for an amazing presentation. There's still a bit of lunch left if you haven't had some yet, and I'm sure Bron will be around a little longer for any questions you may have. Thank you so much for joining, and enjoy the rest of the day. Thank you so much, Bronwyn.